Welcome to Dr. Jimmy's Applied Calculus, still in Chapter 7, moving on with these indefinite integrals coming from either derivatives as a reverse operation or defined in terms of definite integrals varying an endpoint, either way. So looking at indefinite integrals or antiderivatives. And so we looked at reversing derivative formulas. We looked at those basic formulas, powers, exponentials. Now, what about the other rules of derivatives and reversing them? Well, one rule that we can reverse turns into what's in integral form is called a substitution method. So I'll go back. We have different rules for derivative, but we had a chain rule which said if we started with a composition and did the derivative, so find the derivative of f of g of x in terms of x, then we ended up with the product of the two derivatives. So capital F prime times g prime. To actually compute f prime of x, we looked at f prime evaluated at a single entity and then make the substitution u equal g of x to get the final solution in terms of x. So we look at the derivative in terms of the basic substitution u and then substitute back. So that was the chain rule. Now, we can turn that into an integral rule. Well, we switch the order. So, and run this backwards. So instead of the derivative of the left side being the right side, the integral of what was the right side should be the left side before we do the derivative. So all I've done is taken the chain rule, interchange the two sides and writing integrals, getting rid of the derivative. So same rule. So doing the reverse order. So if I know this is the derivative, I should be able to write down where it came from. So we're going to use a substitution for g of x to come up with this, because we'll look at the creature we're after should be f of a basic variable u under substitution. And so in the case of integration, instead of calling it a composition rule, is called the substitution method. So coming from this substitution that shows up in the chain rule or in this reverse integration rule. So the idea is to realize what we're integrating in terms of a single expression, capital F of u, and then substitute back. But capital F of u would come from the derivative. So we're replacing this. If we know it's capital F of g of x, that would be capital F of u under the substitution u of g of x. But then in this formula, notation-wise, it should have come from the integral of the derivative. And so we come full swing that we convert f prime of g of x of g prime of x into f prime of u du. Work out an antiderivative in terms of the symbol u. So now we don't have the extra factors. And substitute back to get f of g of x. So that's our substitution method. So now, when might we attempt this? So the first thing is that we have this set up as a product to start with. So we'll look at something that we can look at as a product. One of the factors in the product, though, is going to be a composition. So we're going to look at a setting where we can divide it into factors, one of which we're going to look at as a composition. And then attempt to write this as f prime of g of x and g prime of x under that setting. So it may or may not work, but that's when we would try this. So, for example, if we had the integral or antiderivative of 5x times the square root of 4x squared minus 7. So, in this example, I see a product of several things. And so, essentially, I want to divide it into two pieces. And of the different things that are multiplied, I notice one of them is set up suggesting composition. So that setting, I would first start with f prime of g of x put in as the possible composition. In this case, the square root composed with 4x squared minus 7. So f prime of a symbol should be the square root of the symbol, which is also u with exponent 1/2. And my g of x then must be 4x squared minus 7. So that's the line of attack I'm going to take to see if everything else fits. So my u substitution is 4x squared minus 7 back into, if I can find a capital F of u. An antiderivative there would come from u add 1 to the exponent, 3/2, divide by 3/2, but that's multiplication by that reciprocal, 2 over 3. So there is, I do know, an antiderivative of the square root of a single symbol. And this is just one of them. At the moment, I'm just worried about finding one antiderivative. At the end, I'll worry about adding the constant. So this is my attempt. If I take my f prime of g of x and g prime of x, that will give me the square root of 4x squared minus 7, which is the one factor I chose to be f prime of g of x. G prime is 8x. So this setup that I'm looking for, f prime of g of x and g prime of x, is 8x square root 4x squared minus 7. In the integral I'm looking at, it's not quite the same. This is 8x times everything. This is 5x. So, but I can adjust coefficients that are constant by, we can divide by 8 and multiply by 5. So, the 5, I'm just introducing this coefficient as 8 over 8. And so the 5 over 8 is a constant. I can bring that out. And now what's left is what I've constructed as capital F prime of g of x times g prime of x. But then we've seen now in this case it's capital F prime of u. Du should end up, after that substitution, the capital F of u. And so I could have substituted that here, square root of u, worked it out, but I did that above. So F in terms of u was 2/3 of u with an exponent 3/2. Let's see, this 5 over 8, I can divide the 2 out and get 5 over 12. U, substitute back in terms of g, 4x squared minus 7 with an exponent of 3/2 plus a constant. So, I had this thing I saw, it's a list of factors. I divide it into 2 parts, and then the suggestion is, well, one of these parts is looking like, and I almost read it off as a composition, the square root of something else. So it's my at least attempt at finding an antiderivative. So I make that my composed piece, which then tells me what the g of x is and what its g prime is. And then I look, is that equivalent to what I start with? And so it might be off by a constant coefficient, which I can compensate. Let's look at another setting. This one is the integral of a rational expression, that is a polynomial divided by a polynomial. So at the moment it's not written as a product of two things, but divisions are really multiplications by reciprocals or negative exponent settings. So I could change this to a product. And so the part with the -1 exponent is the part that looks like a composition of the -1 power of x squared minus 3x plus 8. So that gives me the parts. The capital F derivative in terms of a symbol is u to the -1. The g of x that I'm choosing will be x squared minus 3x plus 8. And so I'll have the other parts. I need g prime, which is, doesn't look so much like an equal 2x minus 3, and an antiderivative. Oh, u to the -1 is the derivative of the natural log. So now we're looking at the pieces. If I look at the integral f prime of g of x, g prime of x under this particular composition and substitution, u equal 2x minus 3. I would have the integral, the g prime is 2x minus 3. And f prime of g of x is the x squared minus 3x. There was also plus 8. With an exponent of -1. So, not exactly what I started with. Which is 4x minus 6, but if I factor out a 2 from the original, I end up with this particular integral. So, using constant coefficients, my integral 4x minus 6 with x squared minus 3x plus 8 exponent minus 1 is 2 of the f prime of g of x, g prime of x dx's. So I will get 2 of these f prime of u du, if I like. And I determine this particular integral as natural log of u. And then, but we had the substitution, u was actually g of x. So x squared minus 3x plus 8.